So hello, let's continue the derivation of the Shockley-Reed-Hall expression, but let's focus first on the capture and emission relationship. So in the previous section, we derived rate equations, rates for electrons to increase and decrease via traps, and for holes to increase or decrease in time via traps. And each of them has two components. Process 1 destroys an electron, process 2 creates an electron, corresponds to these rates, like this. And we had the destruction of a hole and the creation of a hole mediated via trap. Each of these processes changes the state of a trap, like this, from here to here, from here to here, and it changes the accounting or the state of an electron from here to here and here to here. The point is, the view on the left here has nothing to do with accounting of holes in the valence band. The view on the right here is focused on holes and traps, and it has a number of electrons in the conduction band. And that'll play an important role in the derivation that we're now undertaking. All right. Before we do the derivation, let's simplify things slightly. We're going to assume that these semiconductors are non-degenerate. And when somebody says that, like your teacher in an exam, and you're asked to do an exercise or homework, what that means is you assume that the conduction band is empty and the valence band is empty. Meaning, in all of these scattering processes on the left, we will always find an open space for an electron to hop into. So it will not be occupied such that it would block this process. Similarly, we will find an available hole state such that this scattering process can happen. This is not a rigorous definition of non-degenerate, but when somebody says, let's do non-degenerate, this is one of the implications that needs to come to your mind. So when you do that, you basically drop this term and you drop this term. You set the occupation of holes to 1 and the occupation of electrons to 0, meaning 1 minus FC is set to 1. All right. So that's a small modification that'll make some of the symbol shuffling a little bit easier. Now in the next stage, we're going to consider equilibrium or detailed balance. And what we'll do now is we'll attach to any of the physical properties and concepts here a subscript 0. Okay? It means we're considering equilibrium. So we're going to look at electron density as a function of time n0. We're going to have n0 show up here. We're not going to look at the equilibrium number of electrons in the system. And we're looking at the equilibrium number of holes in the system. We're also looking at the occupation of the occupation of the traps in equilibrium. So we will have, again, hole-filled traps and electron-filled traps. And we put the number 0 on them. And that's how they show up in the rate equation. And we have these coefficients, the capture coefficients and the emission coefficients. And we also label them as 0. I'm going over a process here of attaching a 0. What I want you to understand is that each of those may or may not be different from out of equilibrium conditions. Okay? All right. Let's look at the electron process, electron traps. Again, I had made the point that this is 1 unit, This is another unit in terms of talking about electrons and traps and holes and traps. Now let's just look at the electron component. We have one rate equation for this one process. And we're interested in a recombination and generation between electrons and trap states here. Okay? Now, there's other processes that are going on in this semiconductor. There could be electron-electron interactions in the band, and there will be processes where electrons hop up in energy and go down in energy, and the reverse process must also exist. We might have phonon emission and phonon absorption, where a phonon is a lattice vibration that can give energy to the electron, and it can absorb energy from the electron. Again, there must be a forward and a reverse process, if you will. And that's labeled here R5 and R6. There can be transitions from one conduction band into another one. For example, a gamma X transition in gallium arsenide, for example. So there must be a forward and a reverse process, and we can label this forward and reverse process separately if we are careful on really understanding the design and the description of these processes carefully. All right, so these are some samples of processes that could be going on in a semiconductor. And when somebody says steady state, what you can write down is basically whatever you're going to write down in terms of expressions, etc. You're aiming for looking at the time derivative results being zero. This thing is not going to be dependent on time, whatever you look at. So in shorthand, you say ddt is equal to zero. ddt considered in this system would mean all of these processes are summed up to zero. The sum of the processes balance out to zero. Meanwhile, equilibrium is a different beast. Remember, we had drawn some examples beforehand, but let me close here. In equilibrium, each of these sub-processes, like the recombination generation term here, like the electron-electron or electron-phonon or gamma X transitions, each of these processes would have to sum out to zero. That means in this element here, each of these would go to zero, which is very different than having just the total go to zero. And if you remember, we had drawn in a previous lecture sort of trade or people exchange between India, China, and Mexico, like this. And we had said that you can have forward and reverse processes between these countries, and equilibrium meant each of these processes is self-balanced, versus steady state just meant there's no overall change in the whole system. That means if I balance each process, the forward and the reverse must balance out equally. Okay, again, this is the definition of equilibrium, which means each fundamental process that is going on and its inverse must self-balance, independent of any other process that is occurring. That is what equilibrium means. Now, that means So in the past, we have actually used this. This is the slide I just pulled back in where we derived the Fermi-Dirac distribution. We had said that the forward process here must equal the reverse process. Okay? So that was already helpful in deriving the Fermi function. Now we're going to use the same principle to derive a relationship between the emission and the capture coefficients. Because this process here, writing red on red is maybe not the best, but these two processes must self-balance. Okay? So the sum of them is zero. And since we have given them when we design the rates, appropriate signs, there's no, this minus sign I had in the previous nodes falls away. So you basically, these two terms become equal. So the rate of increase is equal to the rate of decrease of electrons in this case. All right. So I'm just going to turn the number of electron-occupied traps, I bring that over to here, okay? Now, what I have here is that the electron emission coefficient is related to the electron capture coefficient by some electron density, okay? So I'm just identifying some objects here. Here's the emission, here's the capture, and here's something that has the units of electron density. Now, I didn't say what that electron density is. I didn't tell you how to compute it yet. But this is the fundamental relationship between an emission. It must match the capture of a certain amount of electrons. That is how you relate the emission to the capture. All right. So we just define a relationship here and call this density N1. Okay? It just, for now, is just a pure definition of just stating that emission and capture are related by a factor of N1. And that N1 is a computable constant. So what is that constant? We had, in the past lecture, calculated the occupation of traps in this form, in equilibrium. Okay, we have the total number of traps. We have something that looks like a Fermi function. It relates the Fermi energy in the system to the level of the traps, the energy level of the traps, and therefore we have an occupation of these electron traps in equilibrium. Occupation of holes of these traps is basically Nt minus the number of electrons in the traps. And we had already calculated an N0, which is the electron density at equilibrium. It's determined by this distribution EF and EI. EI is in the intrinsic level. EF is the Fermi function. And if you have electron doping, the Fermi function is above the intrinsic level. So you have a large number of electrons. And this is a term we had derived in the previous lectures. So we're just going to use those later again. All right. So here we are. We have the expression for the electrons, where we related the emission to the capture by some coefficient. Okay. Now we can do the same thing here for the holes. The math is exactly the same, the arguments are exactly the same, and we have a relation between the emission of holes with the capture of the holes and some hole density. And again, the relationship for P1 is written down here, and it's a calculatable constant. All right. Now, let's look at the relationship between N1 and P1. I'm just looking at the expressions. I multiply those two. Nothing much happened, except you can see there's these terms drop out, and you get N0 times P0, which is, again, the law of mass action at equilibrium. So P1 times N1 is Ni squared. Okay? So it's a really compact expression. The two must be related by the Ni. Okay. So we have, by definition, some terms we wrote down for N1 and P1. And I would like to now derive some more detailed expressions that aim to express N1 and P1 in some more detail. Okay? So we can consider a trap like a donor. It's a donor that would be ballpark mid-gap. But from a mathematical treatment, we can consider it like a donor. and we can assign a probability of an empty trap and call that F00. Okay? And we're wanting to compute these occupations of these traps and derive an expression for that and use that in a later slide. All right. So I had already shown that in equilibrium, the number of occupied traps is calculated like this. The number of, that can then be expressed as 1 minus F00 times NT. Okay? Now, this here is the same as NT 1 plus GD e to the beta and ET minus EF, meaning this guy. Okay? This GD is the degeneracy of these traps, and you can put it into the exponent or pull it out and basically call this an equivalent trap energy. We had done this in the previous lecture. It's really meaning the same thing, you just, in the steps forward, we will use the expression with a GD. Okay, and we call this, just to drop these exponentials, we'll call this G exponential, this GD times this exponential. It's just a shorthand, okay? All right, so we'll use these expressions, and we're going to do some number shuffling here. So we can now express also PT as NT F00 because that's the empty trap probability. Okay? All right. We have the expressions we started from. Now we're going to resolve 1 minus F0. That's the occupation of electrons in traps, or the probability of finding an electron in a trap, as 1 plus Gx. That means F00 is 1 minus that. We can pull that together. So that is Gx divided by 1 plus Gx. It'll be very handy to have this expression here, F0 divided by 1 minus F00 in a later slide. So here it is. We derive the expression. It's just algebra at this stage is Gx. Okay? We will use these terms in just a minute. Okay? All right. So now let's write down N1 in terms of these expressions. N1 is a function of the trap, number of occupied whole occupied traps, empty traps, and number of electron occupied traps. And we had just shown those numbers. This goes here, this goes here. NT's cancelled, and we're substituting in this term. Now, if I just look at this, N1 is related to N0 times some occupation, probability. Okay? So we're aiming for relating N1 to some equilibrium properties. And so I'm just substituting in this guy here, and now I can use my abbreviation and plug it in. Okay? So N1 is now related to the occupation of traps again, okay? With some trap degeneracy in relationship in terms of energetic difference between the Fermi level and the trap energy level. Okay. If I now plug in N0 at equilibrium, we already know what that is. That is an expression that should become very familiar to you. We just plug this in. What we see here is this Fermi function in this product drops out. Okay? That means N1 looks similar in its expression to this N0, but it relates the trap energy to the intrinsic energy, okay, rather than to the Fermi function, or the Fermi energy. All right, so we have an expression for N1 that depends on some specifics of trap energies and trap degeneracies. And it's related to the intrinsic level, which is roughly mid-gap. Okay. We have the law of mass action. We can get P1 as Ni squared over N. Therefore, we can get P1 by plugging this in. And we get an expression for P1. Again, relating the intrinsic level roughly at mid-gap to the trap level energy. Okay. So now we have relationships between emission and capture, and we have that coefficient N1 and P1, and we have expressions for it in equilibrium to physical constants such as the trap degeneracy and the trap levels. Okay? So now what we're going to do is we're going to use these expressions to calculate the occupation of electrons in traps and the occupation of holes in traps, meaning we're going to focus on traps as the mediating object, mediating particle, and derive its steady state population. All right, that'll be in the next section.